Okay, welcome. Now we're going to do our second example, force calculation involving motors for mechatronics class. Here, now I'm looking at example one. I pulled this, from the example one from that homework assignment. It says here that, oh, somebody got dropped. I guess that was Matthew we're saying. He's 3D printing a climbing robot, 2 tracks, total mass of 2 kilograms. He's using 2 15-watt motors, one for each track. So lots and lots of information here. Sprocket of 6 centimeters. He's using ABS, blah, blah, blah. Assuming a reduction of 15 strength, will his choice of plastic shaft work? Consider independently the shaft torque and bending. So it looks like I need to first calculate shaft torque, the torque in this motor shaft for torque, and then the stress for bending. And I'll have to then compare that to what I'm given in an appropriate fashion to see if his 3D printed shaft will work. So let's solve this. So the first thing I'm going to do is a schematic. Always do a schematic first. So our schematic might even have a couple parts. So they told us that Matthew is into climbing robots. So he's got his tracked robot. Maybe it looks like a little tank. It's got some center of mass. And it looks like this thing weighs 2 kilograms. So it's going to be 2 times 9.81 pulling down. I can fast forward that a little bit. I'm going to reduce this problem. It's still climbing, but there's some drive sprocket. Let's assume the sprocket's in the back. I don't know if it matters. So I'm going to transfer this load to the center of the sprocket. So it's here, 2 times 9.81. And let me do this one more time. So now I'm going to look at the sprocket, right? So if I think about the sprocket, just here, it's got some shaft. Again, that load of 2 times 9.81 is here. And similarly, I'm going to have a similar force that keeps in equilibrium. You know that the sprocket's pushing against the track itself or the chain. That's loaded there. And from this guy, by the way, let's see what size this sprocket is. It says that my sprocket has a pitch diameter of 6 centimeters. That's the working diameter. So that means my pitch radius is 3 centimeters. So from this, I can find, there's not going to be any torque caused by this guy, but there's going to be torque caused by that force. So I'm going to get my torque from here. The torque that shaft is going to see as R cross F. I'm assuming R and F are perpendicular. So I can rewrite that as R, 3 centimeters times F, which is 2 times 9.81. That'll be Newton centimeters. And I can do that calculation, and I'll do that in a moment. So that's the torque that I see on this design. All right, now I've got this loaded, I've got this torque loading. Now I'm going to go to a free body diagram of the shaft, because that's what I'm interested in. So this will be my second step. So, I have the motor sitting back here. It comes out to this sprocket, which was loaded out here. Just kind of drawing it in so we can kind of see it here. And I observed that I had a torque acting on the shaft. I'm going to draw my torque like this with a double arrow, or I guess we could say a torque. I'll call that my torque. And then I'm also noticed pulling straight down with this 2 times 9.81. The shaft is circular, so I don't really have to worry about the direction. It's going to be symmetric in any direction. So I can just assume in this case it's pulling down on this. I guess we could think about the direction. Is my motor actually attached to the body? So I'm pulling down with the motor, but we'll just call it here. So I've got my force and my torque, and then if I want to just do this free body diagram one more time, at this end, my shaft is cantilevered, right? I'll just assume it's cantilevered on the motor, at the input to the motor. So over here, I've got this 2 times 9.81. Oh, I just thought of something. You know what? We have 2 tracks. Total mass of 2 kilograms. So I'm going to cross out this 2 since there's 2 tracks. I'm going to divide that by 2. So I guess I should say divide that by 2. Gosh, made little mistakes like that. So let's just cancel out this 2 because we're assuming 2 tracks. 1 kilogram acting on each. Okay, so I've got that 1 kilogram of load there. I've got this torque, if you will, of 3 times 9.81. And then finally, the length of this shaft is also 3 centimeters. Oh, it's a little confusing. And I'm going to have a bending moment coming out of the board. So I'm going to draw that with 2 arrows, or call this M. And that M is also going to be my 9.81, that force times that length, which will be 3 centimeters. So a little hard to keep track of, but there I've got those loads. So I've got these 2 scenarios showing up. I've got this torsion, got this force, I've got this moment. So let's first look at the torque, which is going to result in torsion. And when I look at the unit load on my material, I call that a shear, torsional shear, stress. That's the unit load, is stress. And then I'll also consider the bending stress, because those are 2 cases that I was asked to consider. Okay. So my torsional shear, okay, I jump over to my notes. I guess I should pull them up here, but you have them. Jump over to my notes, and I see in my notes that my torsional shear is given as the torque times the radius divided by J, the polar moment of inertia, which is TR over pi halves. Polar moment of inertia for a circular shaft is pi halves r to the 4th. My bending stress, sigma, is M times Y over I, where in this case, Y is the distance from the neutral axis down or up, doesn't matter, the neutral axis in the middle, so that's Y, which is also, you can see, equal to R. So that's going to give me M, R, I about this, in this case, we got to be going about this axis, so we'll say about the x-axis is given as pi to the 4th over r to the 4th. And you should have that in the updated notes. If you look online, I've updated with a nice table, or we could just do a Wikipedia search or look in our book and get these unit cross-sectional values. Okay. Well, I guess we're ready to start plugging in numbers. So, well, let's see where this is going to end up. Once I get that force, I'm going to then compare that with my, so let's say this will be step 3, calculating those stresses. Let's finish out this step 3. So my torque is going to be T, which I said was 3 times 9.81. And notice that's Newton centimeters. J is going to be pi halves, centimeters to the 4th. And how many centimeters we need to find that? What was the radius of the shaft? A solid shaft, 1 centimeter in diameter, so that's 0.5 centimeters to the 4th. And I realized I forgot the R on top, didn't I? So that's Newton centimeters squared on top and centimeters to the 4th on bottom. So my result here will be centimeters, Newton centimeters squared. And I'd like to have that in pascals, which would be Newton meters squared. So I'll multiply that times, let's see, 100 centimeters per 1 meter. And I want to cancel out a centimeter squared, so I'll have to square that. Okay, and then my sigma is going to be M, which we said again was 3 times 9.81 times Y, which is R, so times 0.5, and again that's Newton centimeters squared, over pi over 4 centimeters, 0.5 to the 4th, so that's centimeters squared. We'll have to multiply that times 100 squared to get Newton per meter squared, or a Pascal. Okay, let's jump over here to MATLAB. Run our numbers for us. So we get 3 times 9.81, oops, times 0.5 divided by the quantity pi halves times 0.5 raised to the fourth. That, oh, I gotta, okay, so, and then I gotta multiply that times 100 to the squared. And that gives me 1.5 e to the 6 pascals, or 1.5 megaPa. So 1.5 megaPa. And that's the shear stress that I see. And then this guy's going to be the exact same, except he's dividing by 2, multiplying by 2. So sigma is going to be 3 megapa. Do we need to double check that? Do we feel confident? I feel confident because I tried it once first to make sure. I'm actually prepared for once. So, well, that doesn't mean I still didn't do a mistake, but I got 3 megapa. Okay. So that's what we see. Now we got to compare it with what we have. So what we have is it says that we have an ABS with ultimate strength of 40 megapa. Well, that's promising because it's larger, but do we compare directly? No, we have to use some failure theory. Failure theory I'm recommending is as a quick and dirty one is a max shear stress theory. Works for ductile materials. Plastic is really ductile. Probably need a better one for plastics, but we use it. Max shear stress theory, and that says that tau max is my ultimate strength, or actually my yield strength, but in this case we're only ultimate, so we're using it for yield. So I'll just say it's my strength divided by 2 times my factor of safety. Now in this case I don't have a factor of safety, but it does say I'm getting a reduction in strength of 50%. So let's put that in here. So that 2 comes from the 3D printing. So it says that the maximum shear is half the maximum strength. And then the maximum stress is going to be 2 times the maximum shear, which is just the strength by itself. And then I'm going to divide by 2 because of our reduction for 3D printing. So that means I get to what was that number, 415? No, 40 megapa. So I get 40 megapa divided by 2 times 2, which is 10 megapa. Okay, is my actual shear stress less than my maximum? Yes. So this shaft is okay for torsion. And then let's come over here. Over here, I have to compare this with my bending stress. So I get 40 over 2, which is 20 megapa. And again, my 3 megapa is less than 20 megapa, so I'm less than my max. I need to write that down. My sigma is less than my max, so sigma is less than sigma max. So it's shaft okay for bending. Yay. Okay. So that's the answer. This problem is independently okay for shear and bending. Now, and that's the end. That's the end of this problem. Let me mention, we simplified that. We independently checked torque and bending. Now in practice, both loads are there. You'd have to combine them. So, you know, we did that in the notes, combining the stresses, but for the first pass on this first mechatronics class, don't worry about it. Just recognize that technically you need to combine these two. It's not adding them, but you need to combine them in, you know, some way, to use an electrical approach. It would be sort of a root mean squared type of combination of sorts. Okay, because we have to look at the vector quantities. Okay.